Okay. So we are live streaming now. Good. Okay. So we'll just wait just about a minute just to see if anyone else will keep joining us for this tutorial on the final exam from 2014-2015. And the other thing too to notice that we do have a chat feature. So I'll occasionally look up at my screen. I should be able to see people talking. And also feel free to, if you know what the answer is and I'm not quickly picking up on that, just you can also respond to other people's questions too. Help them out. Okay. Just I'm gonna grab one more thing and then I'll be right back. Okay, so again, this is all brand new technology to me, so if there's some glitches or something like that, bear with me. It's just the way that it is. Okay, so we got some people who've already started watching. Okay, so what we're going to be doing is we're going to be going through the fall exam that was given in 2014-2015. And this was a 3-hour exam. It was from 9 to 12. And again, you had to answer all questions. The point values were indicated in the right margin. It was a closed book exam. Again, it's going to be the same thing for our exam. You won't have any calculators. You won't have any notes. And again, that's in the third note there. You're going to have to simplify as much as possible, but it should be fine. And the other thing too is make sure that you circle our name on the exam so that that we know that if the books get mixed up, that we can figure out and sort it out. Okay, it helps us out. Okay, so again, we were trying to do some of this in class, but we just ran out of time. So the first question we have is express the following argument symbolically and use a truth table to determine if it's valid or not. Okay, to this, and okay, so that's what I need. So there's the argument that I have. If Bruce goes to the movies, he always gets a large popcorn. Either Martha goes to the movies or Bruce goes to the movies. And the last proposition is Martha will not go to the movies, and therefore Bruce gets a large popcorn. So the first thing that we need to do is we need to denote what our propositions are going to be. So let B denote that Bruce goes to the movies. The next thing is say that P denotes Bruce gets a popcorn. And the other proposition that's in this argument is that Martha, so we'll use M to denote that Martha will not go to the movies. Oh, let's use, we'll scratch that out. She will go to the movies. Okay, so then the argument follows this form. We translate this, that's what it means by we want to express it symbolically. So we have Bruce, if Bruce, so again, we're seeing that this is a conditional statement. If Bruce goes to the movies, B, this implies that he gets a large popcorn, so that's P. So that's your premise. The next one is Martha goes to the movies or Bruce goes to the movies. So I got Martha. This is an exclusive disjunction. So P and or, then followed up with B. This is the premise. The next one is Martha will not go to the movies, so that means not M. So this is the next premise. And therefore, Bruce gets a large popcorn. So that is P. So that's our conclusion. Okay, so just doing that gives us a couple of marks for you guys. Then the next thing that we need to do, just move that up. So I have that. I need to check this using a using a table. Okay, because that's what it says in the question. So just looking for my line. So we have our three prime propositions. We have B, we have P, we have M. And then we have our premise. We have B implies P. We have M or B. And the last one we have is not P, or not M. And we'll use this one for our conclusion. So here are our three premises, and there's our conclusion. So I have three prime propositions, which means that I'm going to have 2 to the 3 or 8 lines. So just neaten this up. Okay, so I have 4 trues and 4 falses. Okay, and the second one I'm going to have 2. I'm going to have 2 trues and 2 falses, and then alternate from that. And again, in the last one, I'm just going to alternate between true and false. Okay. Will this be saved so I can watch it later? Yes, it should be saved. Okay. So now we can do B implies P. So remember with the implication, the only time it's false is if I have the first one is true, and the second one is false. Okay, so true implies true, that's true. True implies true, that's true. True implies false is false. That's false. This is true. This is true as well. This is false. Oops, no. This is true, and this is true. So let's just check that over again. So the only time it's false is this time. So good, good. Excellent. Okay, so in the next one I have is I'm going to be using this column and this column, and I'm going to be doing the exclusive OR, which means that one of them can be true, but not both of them. Okay? So again, here's my 2 that I'm looking at. I have true. This is false. So this is true. This is false because both of them are true. This is true. This is true. This is false. This is true, and this is false. And the last one's really easy because I can actually just take this column and flip the values. So this becomes false, true, false, true, false, true, false, and true. Okay, so let me pick some colors here. So right here, these are our premises. They're so new that they have the plastic tip on it. Okay, so these are our premises. And over here, is our conclusion. Okay, so let me just shift that down. Okay, so remember, for an argument to be valid, I need to have the conclusion be true whenever the premises are true, and they're all true. So I go down here and I look for, here's one where I have all true premises. Okay, the next one, that's false. Nope. Okay, so this is the only case where I have all of the premises true and the conclusion is true. So this means that it is a valid argument. So I have to make sure that I state this. Okay, since all cases where the premises are true, the conclusion is also true. So therefore, the argument is valid. Okay? So that is 1A. The next part of the question is, I scroll up to right about here. Okay, so this one says use the laws of logic. We've been saying them as rules of inference in class, so that's what it means. To determine if the following statement is a tautology, contradiction, or neither. Okay, so a tautology is where it's going to be all true. A contradiction is where it's all false, or neither is when you got a mixture of true and falses. Okay, and it specifically says do not use a truth table. Okay, so you can't prove that statement using the truth table. So let me just rewrite this out. I got P and Q implies And then I'm going to use the square brackets here. P or Q and R. Okay. So the first thing I notice is this. I want to get rid of that implication arrow because all of our rules that we've been using, the distributivity, associativity, the rest of them, they all use disjunction or conjunction. They don't use implication. So remember, our rule for the implication is that P implies Q is logically equivalent to not P or Q. And now this rule, all these rules will be available to you on the final exam, so you can just look that up. But again, it's important that you know how to apply them. So, okay, so converting this by the implication rule. Okay. Make sure that I keep an eye on some of the comments. Okay. So this is by the implication. Remember, I need to see some justification by the implication. The next thing I see is this negation here. I want to distribute inside here. Okay, so when I do that, it goes not P, the conjunction switches to the disjunction, so I get or, not Q. And then I keep my other one here. Okay, so this is by a De Morgan law. Okay, the next thing I have is I'm going to shift these brackets. Okay, so I can actually, because I have an or and an or here, I'm just going to shift them to here. So I get, I'm going to keep this bracket here, or P, okay, can shift that bracket there, or this is by associativity. Okay, the next thing I can do is I'm going to just flip these. I can do this by commutativity, so I got P or not Q. And that's by the commutativity rule. Then the next thing I want to do is I'm going to distribute. So I can take this, well, basically this, and distribute. Oh no. Actually, I don't do it in this case because notice I have an or and an or here as well. So I don't do that. Instead, what I can do is I can just shift these brackets again. So I got P or not P or not Q. So that's by associativity. Okay, then the next thing I can do is I have P or not P, which is a tautology. That's by the excluded middle. So we get tautology. And basically from there on in, it's going to start collapsing. So I get, this is by the exclusive middle, excluded middle. And this is the last, so I have a tautology or or not Q. So that's, I believe, by either identity or domination. Okay, and the last one, again, a tautology or not, a tautology or Q and R. So that's, again, just a tautology, because, again, this dominates. And we're done. We're done that proof. But again, I can't remember if it's by identity or I think it's domination. And same thing here. Okay. All right, so let's see if I can. Exam question. Okay, so this one says, in how many ways can the letters of the word Canadian be arranged? So, yeah. Okay, so there are 1, 2, 3, 4, 5, 6, 7, 8 letters in total. So the number of permutations there are 8 factorial, but we need to eliminate some of the repetitions because we have some letters that are repeating. So for instance, I have A's here. I have 3 A's, I have 2 N's. So let's see. What I'm going to do is, I'm going to divide that by, and just start working them out here. So I have 1 C, so that's 1 factorial. The next one I have is 1, 2, 3 A's, so there's 3 A's there. 1, 2, 3. The next one I have is N, so I have 2 N's. Last I have a D. And finally I have an I. So I have 1 factorial. So really this can simplify down to is 8 factorial over 3 factorial over 2 factorial. Okay, so I can expand this out a bit so that I get I'm going to stop at 3 factorial. 3 factorial there. And I have 3 factorial over 2. So I can cancel out that. And 2 factorial is just equal to just 2. So I can actually divide that into here. So 8 divided by 2 gives me 4. So I'm left with 4 times 7 times 6 times 5 times 4. Okay. So, okay, well, I see 20 times 4. So 20 times 4 gives me 80. And then I'm going to multiply it by 42. Okay, so 42 times 8 gives me 16. And then 8 times 4 is 32, 33. Okay, So again, I should be multiplying that by 80. So it'll be 3,360 ways. Okay. So therefore, there are 3,360 distinct permutations of Canadian. Okay. So going on to the next question, I have let me start out on a new piece of paper. In how many ways can you arrange in a line across a wall I got cut off. 5 distinct paintings, 3 of which are oils and the remaining 2 are watercolors? Okay, so for part B, so if there's no restrictions, I have 5 distinct paintings, it means that I can use permutations. So it means that for the first spot here, see, I can put up 5 paintings here. So in the first spot, I can have 5. In the second spot, remember, here's the and. On the second one, I only have 4 remaining choices. And on the third one, I have 3 remaining. And on the first, second, third, fourth. And on the 5th one, I'll have just 1 left to choose from. Okay, and that's equal to 5 factorial. And just this is something that I'm sure you're familiar with by now, is 5 factorial is just 120. So there are 120 ways to hang the paintings. With no further restrictions. Okay. In part B, if the watercolors must be side by side. Okay. So what you could do is you treat them like you group the 2 watercolors together. Okay? So that means, for instance, here I put the watercolors here, boom boom. That means that I'm going to have, so there's 1 watercolor, then the next one there would be another watercolor there. So I would have 4, 3, 2, 1. Okay, so that means that if I just group those 2 watercolors together, I don't have 5 choices anymore, I have 4. So I have 4 factorial ways that I could put the paintings. Now remember that if I have the watercolors together and I've glued them together, they can actually be swapped. So the number of ways that you can do that here is 2 times 1. So that's 2 factorial. So I get that 4 times 3 times 2 times 1 times 2. So I get 12 times 4, which gives me 48. There are 48 ways to hang the paintings. with the watercolors side by side. Okay. Next. Okay. So a student is taking examination is required to answer exactly 4 out of the 8 questions. In how many ways can the 4 questions be selected if there's no further restriction? So here's 3A. So there's 4, I can choose 4 out of the 8 questions. So that means that I have 8, choose 4. Okay, so that means that I have 8 factorial over 8 minus 4 multiplied by 4 factorial. So then I'm left with 8 factorial over 4 factorial, 4 factorial. 6 times 5 times 4 factorial. Okay. Let's see, can I just use a finer pen? So 4 goes into 8 twice. 6 divided by 3 is 2. And I'm left with over 2. Okay, so... Oh, and then I can divide this 2 by this 2 here. Good. So now all I'm left with is 7 times 2 times 5. Okay, or there's 2 times 5 is 10. So I'm just left with 70. So there's 70 ways the student can do this choice. Okay. In part B, split this over. So in part B, I have to take cases. And this, because it says that if at least 2 of the first 3 questions must be answered. Okay, so here's case 1. This is if the first, this is if the first 2 questions are answered. Okay, so from the first 3 questions, I need to pick 2, and then I'm left with 8 minus 3 choices, and then for the rest of the questions, I'm left with 4 minus 2. So then I'm just left, if I simplify this down to 3, choose 2, multiply by 5, choose 5. Okay, and again, these are fairly simple. So what I'm going to do is I'm going to use my Pascal's triangle. That should be 10, 5, and 1. Okay, so remember we start at the 0 on the left-hand side here. So here's the three row. So 0, 1, 2, and this one is 0, 1, 2. So I'm multiplying 3 by 10, which gives me 30. Okay, for case 2. This is if the first 3 questions are answered. Okay, so this means that I have to pick all 3 of the questions at the beginning, and then I'm left with 8 minus 3 and 4 minus 3 questions. Okay, so I'm going to be choosing all 3 of the first 3 questions. And then, so I'm multiplying, and then I have 8 minus 3, I have 5 questions left here, and I'm going to pick one of them. Again, there's 8 questions, 3 plus 5, and then I'm picking 4, 3 plus 1, so there's 4. Good. And 3 choose 3, 0, 1, 2, 3, so there's one way, multiplied by 5 choose 1, so 0, 1. Okay, multiply by 5. So the last one is simply 5. Okay, now this is important. This is why we need to always keep writing our therefore statements. So adding up the cases together, therefore, the number of ways to answer the questions where at least 2 of the first 3 questions answered is 3 plus 5, which is 35. Okay, so you have 2 cases in this question. Case 1, first 2 questions are answered. Case 3, the first 3 questions are answered. Okay, and then we add them together. Okay. So this one is to help plan the number of meals to be prepared in a college cafeteria. A survey was conducted and the following data was obtained. Okay, so in this one, there's all the data. And I wonder if I can somehow move that over so that you can see it all. Okay, so I have 130 students that ate breakfast, 180 students ate lunch, 275 students ate dinner. How many of the students ate at least 2 meals? Okay. So there's a lot of data in this. So first thing I'm going to do is define your events. Because this is important for us, we have to understand what you're doing, and we need to know what sets. We're going to use the Venn diagram approach in this case. So I'm going to do let B denote breakfast. L denote lunch. And D denote dinner. Okay. Oh, and then U, which is the universal set, we should denote this as well. So that's our universe that we're working in, and that's all the students who were surveyed. So denote all students surveyed. Okay. Okay, so I start drawing my Venn diagram. Okay, and important, this box is a set, and it's our universal set, which is going to denote all the students surveyed. Then the next thing is I'm going to draw, well, I have 3 sets, so that means I'm going to have 3 circles in this. So I have, there's the first one, there's the second one, and there's the third one. Okay. So starting from the inside out, oh, before that we should label this. So we have breakfast, we have lunch, and here's dinner. Okay, so starting in the middle, oh, let's see, the magic of technology. Okay, there's 60 right there, right? So I'm going to fill that in here because that's where all the students ate all 3 meals. So 60 of them had breakfast, lunch, and dinner, followed by 90 students ate lunch and dinner. So lunch and dinner is right here, but 90, you want to remove the 60 here. So 90 minus 60 is 30. Okay, so so on the test you could, let's see if I can do this. Nope. There we go. I did that one. Now I've done this one. Good. And the next one, I have 100 students ate breakfast and dinner. So breakfast and dinner, so that's this one right in here. So I have 110. So 110 minus 60 gives me 50. Okay, so I've now used up this information here. The next thing I have is 68 students ate breakfast and lunch. So that means it's this one right here, this area in here. So I have 68 minus 60, so that just leaves 8 students. Okay, so I've used up this one. Oops, there we go. And last, I have 3 more pieces of information. I have 275 students ate dinner, so I have dinners here. So I'm going to have 275. So 275 minus 50 minus 60 minus 30. So I'm left with 135. Okay, so that's dinner. The next one I have is 180 students ate lunch. So 180 minus 30 minus 60 minus 8, that gives me 82. And the last thing I have is, oops, so I checked that off. And the last thing I have is 130 students ate breakfast. So that's 130 minus 50 minus 60 minus 8, so I'm left with 12. Okay, so now we can go on to part A. Now, see, and I did that. Good. So the next part of the question is this. Oops. Okay. How many of the students ate at least 2 of the meals in the cafeteria? So that can be at least 2 or 3. So that's all of this in here. Okay. So that's 8 plus 60 plus 50 plus 30 If I add that up, it gives me 148. Part B, exactly 1 meal. So that's just this one, these numbers here. So that's 12 plus 82 plus 135, which gives me 229. Okay, only dinner in the cafeteria. So dinner is right here. So that's easy. We just read that off, 135. And I guess if you really wanted to show, make sure that I knew what you were talking about. There it is. And D. I'm left with exactly 2 meals in the cafeteria. So it's just this, and this here. So that's left with 50 plus 30 plus 8. So I'm left with 88. Okay, so we've done question 4. Okay, so we're told that let A and B be 2 events with probabilities 0.2, 0.6, and the intersection is 0.1. Determine the following if A and B are independent events. Okay, so I'm going to write that down. This is my given information. Probability is 0.2. Probability of B is 0.6. Okay. Okay, so for A, if A and B are independent events, then the probability of A intersect B is equal to the probability of A multiplied by the probability of B. This is only if they are independent. Okay, this is so important because so many people will mix this up between that and this between using the principle of inclusion exclusion. Okay, otherwise, there's a lot of things that people mix up. So only use this as if they're independent. Remember, and then the other thing is people mix them up if they are mutually exclusive. Okay. If they're mutually exclusive, this means that I have 2 sets, the set A and B. These are called mutually exclusive sets, and there is no intersection. Okay. The intersection is empty. Okay, so this means that A intersect B is empty. So that's the empty set. Okay, so then the probability of A intersect B, since there's nothing inside of it, has to be 0. Remember, the probability is a number, and this is a set. Okay, so this is 0, and there's the empty set. So be careful that you know the difference between independent and mutually exclusive so that you didn't just write down the probability of A intersect B equals 0. So in this case, we're assuming you're told in this case that they're independent. So if they were independent, we can just multiply these probabilities together. So 0.2 multiplied by 0.6, okay, which equals 0.12. Okay? But this is not equal to 0.1, which is actually what the intersection is. Okay? So therefore, the events A and B are not independent. Okay, so we just showed that. Okay. Well, maybe I can use part of this overlay. Just a new piece of paper there. Okay, so this time we're asked what the part B, what the probability of A union B is. Okay, so in this case, this is the principle of inclusion exclusion. So it's the probability of A plus the probability of B minus the probability of A intersect B. So I just 0.2, I'm just substituting the values here. I have 0.6 for the probability of B minus 0.1. So I got 0.8 minus 0.1, so I'm left with 0.7. So that's the probability of the union, or A union B. Okay, move that out of the way. Okay, so here's C. The probability of A prime union B primed. So what we could do is we can do this. We can use a Venn diagram. There's A and B. So it's everything outside of A okay, and also everything outside of B. So everything, so I've everything outside of B. So actually the only thing that isn't filled in is in the center right there. The intersection, which we also know to be is 0.1. So you could do it this way, 0.1. Or if you prefer a more an algebraic approach, so this is more like a visual approach, the other way is just an application of De Morgan's law. So this is equal to A intersect B, all primed. And then we take the complement of that, so 1 minus the probability. Uh-oh, maybe I did make a mistake there. That's good that I caught that. 1 minus 0.1 gives me 0.9. Right, so this makes more sense because, again, the only area that wasn't filled in is 0.1. So again, it's all the area that needed to be shaded in. So there's the 0.1, but really, it's everything outside of it. And the entire area, remember the probability of the entire sample space is 1. So it's 1 minus the 0.1 right there. So that is just 0.9. Okay. Part C. Okay, we did part C. Now on to part D. If I can move this up a bit. part D. Okay, so it's the probability of A intersect B. Okay, so it's A, everything in A that intersects B prime. So everything outside of B. So it's just this right here. Okay, and to get that area, what I need to do is the probability of, so I'm taking all of A minus, and then the intersection of A intersect B. So that's 0.2 minus 0.1, which gives me 0.1. Okay. Next one. Let's see. Okay, so now to do part E. So we're asked to find the conditional probability of A primed given B primed. So that's equal to the probability of A primed intersect B primed all over B primed. Now we already solved, did we solve that one already? No, we didn't. Okay. So what I'm going to do is I can apply De Morgan's law in this. So I can do the probability of A union B, all primed, divided by the probability of B primed. And that's equal to, now I can take the complement. So 1 minus the probability of A union B divided by 1 minus the probability of B. Now we calculated this. 1 minus the probability of A union B is equal to 0.7. And the probability of B is 0.6. So I'm left with 0.3 over 0.4. And that's equal to 0.75 or 3/4. Okay. And I think, let's have a look. Do I have one more for that? I do. Here's the probability of A given A union B. Okay, so that's equal to the probability of A intersect A union B, all divided by the probability of A union B. And if I draw this out, the set that intersects A union B is just A. So that just simplifies down to A over the probability of A union B. So we know what that is. That's 0.2 divided by, and we had 0.7. And so you can put that as 2/7. And you're done that question. see if I can. The next question was the hard one that we did in class. This one is talking about an experiment, and this uses also conditional probabilities. So let me move to a new piece of paper for this. So it's a box initially contains 5 white beads and 5 red ones. An experiment consists of the following steps. You roll a fair die twice in succession and observe the sum of the 2 upper face numbers. If the sum is less than or equal to 4, you randomly select one bead from. Okay, so the first thing we should do is we need to draw the probability tree. So on the first part, I have I'm going to roll a die. So I'm going to have three branches in this case. So I have the sum is less than or equal to 4. The next one I'm going to have is the sum is equal to 5, 6, 7, 8, 9. And last I have a sum that is greater than or equal to 10. And again, like I was doing in class, don't skip sometimes the dumb step, which is what I'm doing right now, which is because I'll forget some of the numbers. So if I'm just adding up the 2 numbers, I have 1, 2, 3, 4, 5. Okay, so the probability that it's less than or equal to 4, right here. So 1, 2, 3, 4, 5, 6. So that's 6 out of the total 36. The next one is, let's do this one. The sum is greater than or equal to 10. So, oh, I forgot a line there. Okay, so in this case, I have greater than or equal to 10. So right here, 1, 2, 3, 4, 5, 6. 6 out of 36 here. And then everything in the rest here. You don't really need to count that because you know it's 6. So 6, that's 12. So it's 36 minus 12. So you should have 34 over 36. Okay. Good. So I don't need to use that anymore. Okay. So the next thing I need is let me just try to scroll up. So I've done that. A fair die is twice. So observe, randomly select one bead from the box. So in this case here, I can select one bead, so I only have to select one. So there's, I'm going to label red, and here's white. Okay, the probability of drawing a red bead is, it's going to be 5 out of 10. There's 10 in total, and same thing with the white. You have equal chances of drawing that. Okay. And the next one, let's see. If the sum is greater than or equal to 10, we randomly select 2 beads from the box without replacement. Okay, so that's important. So I'm picking out the box, the beads from the box, and once I pick it out, I'm reducing the number of beads that I can select from that. Okay, so that's on this one. So again, I have the same kind of probabilities here. I have red, I have white, red and white. Okay, so again, the probabilities of picking a red is on the first draw is 5 and 10, and 5 and 10 on the white. Now in this case, I have one less bead to choose from. And if I picked a red on the first draw, there's 4 remaining left on the red and 5 remaining whites. Okay, and again, this one, if I picked a white, then there's going to be 5 remaining reds on the second draw, and there's going to be 4 remaining whites on the second draw. What I'm going to do is, I'm going to, so I've drawn my probability tree, so I've done that. Because, and the other part is the sum is equal to 5, 6, 7, 8, 9. Nothing happens, so you don't draw anything. So that's, you don't draw any beads. Now notice in the question that B and C all concern about drawing red beads. So calculate the probability that at least one red bead is withdrawn from the box. Okay, conditional probability that the sum is given at least one red bead. Okay, so what I'm going to do, right up here is going to be the number of red beads. Okay, so here, I've drawn 1, there's 0 in this case. In this case right here, there's 0. This case I can draw 2, I can draw 1, I can draw 1, and then there's 0 here. Okay. So part A asks us, what's the probability at least one red? Okay, so in this case here, I have this one case right here. So I get 6 and 36 multiplied by 5/10. Or, so I use a plus. The next one I see here is right here. There's 2, so that's greater than 1, so I can use that one. So I got 6 and 36 multiplied by 5/10 multiplied by 4/9. Okay, so I've done this one right here. The next one I have is 6 and 36 multiplied by 5/10 multiplied by 5/9. So I've done this one, and I have one last row to do, plus 36. I have multiplied by 5/10 multiplied by 5/9. Okay, let me just move that up. So what I can do is, I notice here I have all these right here. They're all the same. So I can factor that out. So 6 and 36 multiplied by 5/10 is equal to 1 plus 4/9 plus 5/9 plus 5/9. Okay. Okay, so 5 plus 5 is 10 plus 14. So I got 14. And then I can change the 1 into 9/9. So I get 23/9. And I can also reduce the 6/36 to just 1 and 6. Can reduce the 5 and 10 to 1/2. So I get 23/9. 23 is prime, so I know I can't reduce it any further than that. So I get 23. 6 times 2 is 12. 12 times 9 is 108. Okay, so that's the probability of at least one red. Okay. So let me just put the exam question back up. And the last one I have is calculate the conditional probability that the sum greater than 10 given that at least one red bead is drawn from the box. Okay. So that means in this diagram, given that there's at least one red bead in the box, well, we calculated this. We've calculated that probability. What this is asking for is in C, the probability that the sum is greater than 10 given that there's at least one red bead. Okay, so that's equal to the probability that the sum is greater than or equal to 10 and at least one red bead. Oops. Red bead. Okay, and then it's all over the probability at least one red bead. Red bead. Okay. So in that case, what I need to do is I'm just going to use these three cases right here. Okay? So I need to use this case here, I need to use this case here, and I need to use this case here, because that's where the sum is greater than or equal to 10 and at least one red bead. Okay, so I need to use these ones right here. So in fact, there's our probabilities right here, and right here. So let me turn off the exam question so I have some more room. So I just need to write those on the numerator. So And we won't have to recalculate this because we've already done that right there. So that's just 23 over 108. Okay, so I won't recalculate that all over again. And again, I get, let me just do with this on the side. So I get 6 over 36. I can factor out the 6 over 36 and the 5/10, so that I'm just left with 4/9 plus 5/9 plus 5/9. So I'm left with 1 and 6 multiplied by a half, and then I have 14 over 9. So I have 14 over 108. Okay, so 14 over 108 divided by 23 over 108. Okay, I take and multiply by the reciprocal, so that I'm just left with 14 over 23. And that's the probability. Okay. Let's see the next question. Oh yes. There's a question that will probably more than likely show up on the final exam, because they have been showing up for the past 5 years. So here's question 7a. We're given that this table here. Ooh, okay, so I'll imagine it here. And what it says is what should the value of A be? So what's this value of A should be here? You have to remember that the probabilities in a distribution have to sum up to give you 1. So remember that the sum of all that the sum of all the probabilities have to give you 1. Okay, so this means that I have 0.1 plus 0.3 plus 0.2 plus A plus 0.1 is equal to 1. So again, A is equal to 1 minus 0.1, 0.02, 0.3 minus 0.1. Okay, so this gives me 0.7. So A equals 0.3. Okay, and that's your reason why the probabilities in a distribution must sum to 1. Okay. So, with the miracle of science, that should be 0.3. Okay, so then B is asking about give the formula for the expected value or the mean and compute it. So what I'll do is I'll just okay, so that's part B. So the formula is the expectation of x is equal to the sum of all the values of x such that it's x multiplied by the probability of the value of x. Okay, so I get 1 multiplied by 0.1 plus 2 multiplied by 0.3 plus 3 multiplied by 0.2 plus 4 multiplied by 0.3 plus 5 multiplied by 0.1. And again, on the arithmetic on this should be straightforward on the final exam. So you get 0.1 multiplied by 2 times 3, that's 6, so it gives you 0.6. 3 times 2 is 6, so 0.6. 4 times 3 is 12, so 1.2. And 5 multiplied by 1, so you just get 0.5. Okay, so then when you add that all up, you should get 0.3. Okay, so the next part is give the formula for the variance of x and compute it. So, part C. Remember that we like to use this version of it. So the variance is equal to the expectation of x squared minus the square of the expectation. So in this case, we need to calculate what the expected value of x squared is. Okay, so there's the formula for the expectation of x squared. So that's all I do is I take these values here and square them, and I'm multiplying by the probabilities. So in this case, I get 1 squared multiplied by 0.1 plus 2 squared multiplied by 0.3 plus 3 squared multiplied by 0.2 plus 4 squared multiplied by 0.3 plus 5 squared multiplied by 0.1. So I get 1 multiplied by 0.1, I have 4 multiplied by 0.3, I get 9 multiplied by 0.2, 16 multiplied by 0.3, 25 multiplied by 0.1. 1 times 0.1 is 0.1, plus 4 times 0.3 is 1.2, plus 9 times 0.2 is 18, so 1.8. 16, oh, I always keep forgetting what that is. So it's 16 times 3, so that's 48, so that's 4.8, and 25 times 0.1, so it's just 2.5. So if I add that all up, okay, I got 0.1 plus 1.2 plus 1.8 plus 4.8 plus 2.5 gives me, I think it's 10.4. Okay, so then the variance is equal to 10.4 minus the square of the expectation, so it's 3 squared. So I get 10.4 minus 9, which gives me 1.4. Okay, and last but not least, I'm asked to give the formula for the standard deviation and do not compute it. So all you have to remember is that the standard deviation of x is equal to just the square root of the variance. Okay, so that's just equal to 1.4. And you're done that question. Okay. check to see if there's any. Nope. Okay. Okay, so consider an experiment of a game where 3 coins are flipped at the same time. Coin 1 is biased, so it's not fair. It's got a probability of 0.8 and a tail of 0.2. Coins 2 and 3 are fair, so that means they'll land on heads or tails with equal probability. Yeah, so it says that right there, i.e. the probability of head is equal to the probability of tails, which is equal to half. Okay, so first question is the sample what is the sample space for this experiment? Oh, nuts. This one's going to be tedious. So this one is saying, what's the sample space? So on, let's say, here's coin 1, here's coin 2, and here's coin 3. Okay, so here's head, here's tails. On the second coin here, I can have heads or tails, heads or tails, heads or tails, heads or tails. Okay, so then I'm going to slightly abuse my notation so that I'm going to go S is equal to, so that's my sample space. I have head, head, head. In this case, I have head, tail. Oops, I'm going to go head, head, tail. Head, head, tail. This one I'm going to do head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, and last tail, tail, tail. Okay, so there is my sample space for this experiment. The next part is this a uniform sample space? And the answer is no. And then it wants me to explain. Okay, so this is not a uniform sample space since the outcomes do not all have the same probability of occurring. Okay, so that's a fairly big claim, since not all of them. So I should back this up with some evidence. So my evidence for this is I could consider the probability of heads, heads, heads. Now, because the probabilities are independent, because I'm assuming that the coins don't affect each other, that if I did heads, there was an 8 out of 10 that the one coin is going to land on heads, and the rest would land on tails, or land on heads with probability 1/2, 1/2. So that gives me a probability of 8 and over 40. Right? 4 times 10, good. And the probability of tails, well, if the one coin is lands on tails, it's 2 over 10, and the rest are 1/2. So I'm left with 2 over 40. So again, it's clear that the probabilities are not the same. So not the same probabilities. Hence, not a uniform sample space. Okay. And let's see, I think I could just flip this over and use that paper and see. Let y denote the number of tails obtained in one repetition of this game. Determine the probability distribution of y. Oh, okay. So I need to calculate. Okay, so what I'm going to do is I'm going to assume that coin 1 is going to be the biased one. So in that case, I can label this with probabilities 8 over 10 and 2/10. And the rest is 1 over 2. So this is the biased coin. Okay, so they want the probability distribution, so that means let me just write it down. So that means let y denote the number of tails So the number of tails in this, I have 0, here's 1, there's 1 right there, there's 2 tails there, there's 1 tail there, there's 2 tails there, 2 tails there, and then there's 3 tails here. Okay, so what I need to do is calculate the probability. So there's the probability of y is equal to 0. And there's only one case in this. So I have this one right here. 8/10 multiplied by 1/2 multiplied by 1/2. Okay, so I have 8 over 40. In this case, I have 1, 2, 3 cases where I have 1 tail. So following this one right here, 8/10 multiplied by 1/2 multiplied by 1/2. Okay, so there's that first one there. I have another one where I have this following this branch. So 8/10 1/2 multiplied by 1/2. And I have this one right here following this branch right there, and I have 2/10 multiplied by 1/2 1/2. So that's 8 over 40 plus 8 over 40 plus 2 over 40, which gives me 16 plus 2 gives me 18 over 40. The probability of y equals 2, I have 3 cases, 1, 2, 3. So following this branch here, 8/10 multiplied by 1/2, 1/2. Okay, so I did that one. Okay, so I need to do 2/10 here. 1/2, 1/2. Okay, I have another one right here. So it's following this branch here. 2/10 multiplied by 1/2 plus 1/2. And the last one that I need to do. Okay, so I've got the 3 cases, good. So again, this is 8 over 40. This is 2 over 40. There's 2 over 40. So I'm left with 8 plus 4 gives me 12 over 40. Oh, I'm almost done. Okay. And it's just this last branch here, right here. So for 3, it's 2 over 10 multiplied by 1/2, 1/2, 2 over 40. Okay, so then just a nice, since you're used to seeing it in a probability distribution, here's the value of y. Zero, 1, 2, 3, 8 over 40, 18 over 40, 12 over 40, and 2 over 40. Okay, and just as a quick check, 8 plus 18 plus 12 plus 2 gives just 40. So it all sums up to 1. Okay. And part D. Ah, perfect, because I'm going to need that part, because suppose that you win $10 if y equals 3, $2 if y equals 2, and -$5 otherwise. Okay, so here's money. So I get $10 if I get, if I y equals 3, get $2 if y equals 2. I get -5 for everything else. That doesn't. Okay. Suppose you play this game. Support your answer by the appropriate. Should you play this game? Basically, he's asking, like, are you going to win money on this? Or is it a fair game? So, let's see. You can just figure out the expectation of this. So here's the expectation of y, which is -5 multiplied by 8 over 40 plus, -5 multiplied by 18 over 40 and 2. Oh, really, this isn't. I shouldn't consider this to be the expected value of y, but it's of this game. 2 multiplied by 12 over 40 plus 10 multiplied by 2 over 40. So I get 5 times 8 is 40. 18 times 5. Okay, well, 18 times 5 is 90. Plus 24 over 40 plus 20 over 40. So minus 40 minus 90 plus 24 plus 20. 86 over 40. Oh, making me do math. 86 over 40 is, well, it's 2 point, wow. Wow, we can just simplify that. 43 over 20. And oh, you can't see what I'm doing. I'm just doing it the long way. And then 20 goes into 100, it goes into 5 times. So that's equal to minus 2.5. So, no, the answer is don't do it. And the reason is because it's negative. So, on average, you expect to lose $2.15. So no, don't play it. Okay. Oh, there's some military questions. Good. Okay. So a large lot of ammunition has been in storage for 10 years and is known to have a defective rate of 20%. 5 rounds of this ammunition are selected at random and tested to be fired. Okay, sounds good so far. So part A is asking you if X denotes the number of misfires that occur during the test, explain why X has a binomial distribution. So again, this goes back to our 3 assumptions that go into the binomial distribution. The first one is independence. We assume, they call it a round, okay. We assume each round does not affect one another. Good. We also know that it's a binary outcome, so there's 2 outcomes. And we label a misfire, in this case, a success. And an accurate, I guess, a fire as a failure. Okay, and the trials are identical. Okay, so the experiment is not changing. Okay, so those are the three things that you need to put on this when you're explaining why a random variable is following a binomial distribution. Okay. Part B is asking about what is the probability that exactly 2 of the 5 rounds misfire. Okay, so from our question, it's important to highlight that our probability of success is 20%. So probability of success is 0.2. Okay, and we're told that there are going to be 5 rounds tested, so that's our number of trials, 5. And that's all that we need for us to start to calculate what the probability of exactly 2 misfires is going to be. So the probability that x equals 2 is equal to, now just to remember, some people just usually will remember a formula. So it's the number of trials, choose x, multiply by the probability of success to the exponent x, multiplied by 1 minus p, so that's the probability of failure, and then n minus x. Okay, so we have 5 trials. We want to show that 2 of them misfire. The probability of this happening is 0.2, and that we want to have 2 of those happen. The probability of failure is 1 minus 0.2, so that gives us 0.8. So, and the last one is n minus x, so that's 5 trials minus 2, which gives us 3. Okay. And again, 5 choose 2. We can always go back to our, I thought I had it. All right. 5 choose 2, 0, 1, 2. So that's 10. Okay. 0.2, or 2 squared is 0.4. Okay. And we got 8 cubed. So that is 60. So 8 times 8, that's 64. Multiplied by 8 gives you 512. And then you're going to do that 1, 2, 3. 1, 2, 3 times. So it's multiplied by 0.512. Okay. And then I have 0, 4. So 4 times 2 is 8, 4, and 20. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then I multiply this by 10, so then it shifts the decimal to here. So it's 0.2048. Okay? Hopefully. Part C. Let's see if I can cover that up with some paper. Part C. What is the probability that at least 1 round misfires? So the probability that x is greater than or equal to 1. Okay, so I have 5 rounds in total, so I can have probability of x equals 1, the probability of x equals 2, the probability of x equals 3, the probability of x equals 4. Oh, that's a lot of writing. but if you realize that you could just look at this as the 1 minus the probability of x equals 0, we only have to calculate one of these instead. So that saves us a lot of time. So I can get home earlier for Christmas. Okay. So again, I can plug in my values here. The probability of 5, choose 0, multiplied by 0.04 to the 0, multiplied by 1 minus 0.04, so that's this should be 0.2. And over here should be 0.8 to the 5th. So get 1 minus 5, choose 0 is 1, and 0.0 to the 0 is 1, so I'm just left with 0.8 to the 5, which is, wow. Okay, so let me see how I can do this. That's a huge. Yeah, 6 times 64 is 256. Times 8. Times 8. Ugh. Almost there. 16,384. 32,000. Yeah. No. 1638 times 8. Did I do it? 1, 2, 3, 4, 5. Oops. Don't have to do it more than that. 1 minus, wow, 16,384 all over 10 to the 5. So that's 100,000. So then 100,000 minus 16,384 gives me 83,616 all over 100,000. Okay. And, oh good, something easy. Let me see. That back up. D. What is the expected number of rounds that will misfire? If you remember your formula for the expected value for the binomial distribution, it's just n multiplied by p. So in this case, we had 5 rounds, and the probability that they would misfire is 0.2. So 5 times 0.2 gives us 0.1. Good. Oh, we're almost finished. We have one last question. I said I would do this in 2 hours. Might flow over. If I want to explain this well, I might take a little longer than the 2 hours. Oh, okay. And last but not least, on a final exam of a certain course of several hundred students, the professor observed that the mean or the average mark to be 68. So that means our expected value is 68%. And we have a standard deviation of 12%. So let's go 12. If the marks are assumed to be normally distributed, which is what we're going to assume, what fraction of students failed the course if the pass mark was 50? So what we're asking is what's the probability that x, oh, we should do that too. Let x be the mark of a student which is normally distributed Okay, so they want the probability of the marks, which is x, to be less than 50. Okay. Now, remember, we need to convert this to be able to use this table here. I need to be able to change it into z. So, to do that, remember that z is equal to x minus mu over the standard deviation. So we got z, which is less than or equal to, so 50, oh yes, minus 68, which is our average, over 12. Okay, so then 50 minus 68 is 18 over 12. So that gives you, and if you get really stuck, again, go back to your long division. 12 goes into 18 times once, so 12. I have 6 left over, and the number of times 12 goes into 60 is 5. Okay? And remember, this is a minus sign right there. So the probability is less than or less than negative 0.5. So then I go to this, and remember how to read your table. So I need to look up, let's see if this, nope. Okay, so in this case I'm looking for negative 0.5. So there it is right here. And I'm going to look under the first column here because I have the 0. So 0, 0, and there's the 0.5. So in this case, I want this right here. I want that number right there. So that's it. So I just write that number down, which is 0.0668. Okay, so therefore the fraction of students who failed is 6.68%. Okay. The next part is part B, which is a fraction of students who got an A, which is 92% or more. So I want the probability that X is greater than 92. Okay. So again, switching this over to Z value, I got 92 minus 68 over 12. Oops. 92 minus 68 is 24, yeah. Over 12. That's much easier. So I got Z is 24 over 12 is just 2. And because the table is set up, because with a less than sign, I have a greater than, I have to take the complement. So 1 minus, and then I look up my 2 value, which is right here. In that case, it's 0.9772. And then I just simply subtract that. So I got 1 minus 0.9772, which leaves me with 0.0228. So therefore, 2.28% of students got an A+. Oh, and then the last one, C. What fraction of students obtained a mark between 62 and 74? So the probability of X being between 62 and 74. Okay, and the way that I would do this is I have to break this down that it's, here's my 68, 62, 64. I need to take all the area up to 74. So all the area up to 74, and then I'll subtract all the area below 62. Then I convert to my Z values, so I get 74 minus 68 over 12 minus the probability of Z over, less than, I get 62 minus 68 over 12. So then 74 minus 68 gives me 6 over 12. And then I'm left with 62 minus 68, which gives me -6. Perfect. Okay, so the probability of Z less than, it's a half, minus the probability of Z less than a -0.5. Again, I just look up my values here. So I got 0.5, so the positive one right here, so it's 0.6915. Minus, and then I look at the negative value here, so I got -0.5, which is 0.3085. Okay, and then I'm almost done, so I have 0.6515 minus 0.3085, which I'm left with then is 0.3830. Okay, and don't forget the final conclusion. Therefore, 38.3% of students received a mark between 62% and 74%. Okay, and we're all done. So I hope that's helpful. You will have this on the final exam. You'll have the standard normal table available to you so that you'll be able to use it. And we were able to complete the exam in under 3 hours, and we did it in about 2. Okay, so that concludes the tutorial, and if you have any more questions, feel free to send me an email, and hopefully if you have any more questions I can resolve it that way, and then we'll also try to set up another tutorial where I'll do this in person. Okay, so thanks again for tuning in, and I hope you guys all have a great time, and good luck studying. Okay, take care.